Okay, well, welcome back to our course on system engineering. This lecture is going to be the last chapter in this introduction and overview and some of the basic knowledge of system engineering as Budi laid out. And we've also tried to introduce some other material from various other textbooks that we're leveraging in this course. In our last lecture, we discussed discrete mathematics, and we gave some general insight into sets, relationships, and functions, how we can partition things into groups, and shows how this can be used for functional definition analysis and requirements analysis. And in this chapter, and as we get into graph theory, we're going to be talking about this from a slightly different point of view and hopefully introduce some material that may be a little bit more easy to understand how it would be relevant. So as a overview, Chapter 5 extends discussion of what we talked about in discrete mathematics to the area of graph theory, so that the graphical communication structure commonly used in the engineering of systems can be seen to have substantial problems as rigorous mathematical representation. So you have the graphs, then you can have the math behind the graphs. So oftentimes it's easier to understand the graphs, and so that's what we're getting into here. On the other hand, the difficult concepts in Chapter 4 can be effectively represented with graphs for analysis and communication. So that's also something that will be useful. So we're going to be introducing the mathematics of graph theory, the formal representation of relationships or functions among elements of a set or a pair of sets. A graph in mathematics is a set of nodes and a set of edges between pairs of those nodes. The edges are ordered or non-ordered pairs, or a relationship that defines a pair of nodes for which the relationship being examined is valid. So a graph enables us to visualize a set, visualize a relation over a set, which makes the characteristics of relationships such as transitivity and symmetry easier to understand. The reader will hopefully comprehend the power of visualizing mathematical concepts as enabled by mathematical graph theory by the time that we're done with this chapter. So in terms of basic terminology associated with graph theory, we're going to introduce that. Notions such as paths and cycles are key to understanding the more complex and powerful concepts of graph theory. There are many degrees of connectedness that applies to a graph. So we'll get a chance to get an introduction and hopefully understand these types of connectedness and how this would enable an engineer to understand the basic properties that can be defined for the graph representing some aspect of his or her system. The concept of adjacency and reachability are the first steps to understand the ability of an allocated architecture of a system to execute properly. So a graph consists of vertices and edges. And so there's various ways that you can be thinking about that, but I'm just going to focus on that and just continue on. So think of a graph that it has vertices and edges, and we'll start to see how that's played out. There's a certain kind of a graph called a digraph or a directed graph, where it's not only showing that there's a relationship between elements, but you can say there's like a one-way street that's laid out. And so the edges in a digraph represent an asymmetric or asymmetric relation. So you can see here, you can think of a program evaluation review technique, a PERT chart, where you have this is a digraph where you can go in one direction. You're going from an input to an output. And so here we have a couple things that are done in parallel, and then eventually they all converge to the end game of what you're trying to do in a PERT chart. And so schedules or critical path are examples of how that can be useful in system engineering. Here is an example of a digraph for is the parent of, and you can think back in the patriarchs in the Bible, So think of Abraham, Isaac, and Jacob, and we have the father of Abraham being Terah. And so here where we're seeing the male line on the right, and we see the female, the wife relationship over here on the left. And so several other related players that are tied into that family tree. And so here we're seeing a family tree, maybe not done in the way that you're used to seeing it, but just trying to show this in the quote simplest way of doing that with a digraph. So here's another example of a PERT chart. And so we have a couple different paths that are taken going from an input to an output. And so we have the design of the hardware and the software. And so this is just another example, a lot more detailed than this rather high level abstract concept of a PERT chart, something that may be a little bit more realistic to lay out how we can be using a digraph to be doing some critical path analysis for a design activity. This is tying in a couple of things here. So I'm showing a state machine diagram up here in the top middle of this chart for a satellite orbital control system for a CubeSat that is derived from something that's from the SysML Distilled textbook for a satellite control system. I'm also using a mathematical tool, an open source tool, to show how we can actually generate a digraph, and that's what's shown here when we take the logic that's laid out here in this satellite orbital control state machine, and how if I was to put that in an equivalent, which would be the format for putting it in SageMath, this is what it would look like, and this would be the output. So basically you have, this is the input, and you have the final termination output in various states going in between here. And so this digraph is a functional equivalent of what we're seeing in this state machine diagram. So we have some more definitions: cardinality, order, size, incident of edges, degree, out degree, in degree, and adjacency. And so these are some of the details that we want to start to be laying out as we're starting to figure out and have the nomenclature of what goes into relevant features for graph theory. I need to try and keep this at a high level, so I'm not going to focus on this in detail, but I'm going to be focusing more on some of the graphs here. So here is a special kind of a digraph, a bipartite graph, whose set of nodes can be partitioned into two sets, A and B. And so here we're seeing how you can go this path and get to an output, or you go B and get to the output of B. And this is such that A and B has no edges connects a node in A to another node in A, and similarly no edge connects a node in B to another node in B. So they only have this one common element here that's shown in that picture. We have several definitions for paths and cycles, the way how we can go from one point to another in a digraph. And so a walk is a digraph in a sequence of one or more nodes. A walk may revisit the same node more than once. A walk is closed if its initial and final and vertices are the same. A path is a walk in which each node is distinct. A trail is a walk in which each node is distinct. A circuit is a non-trivial walk with no repeated edges. And a cycle is a circuit in which all the nodes are distinct except the first and the last. So you traverse back to the same point where you started from. So here are just some examples. So we have a digraph with a walk on the top one, and And this is from the textbook figure 5.4, and on the bottom figure 5.5 is a diagram with 2 cycles and a circuit. So we see how this is some interesting and complex connectedness, still with relatively simple diagrams that we're seeing laid out. Okay, we have some more nomenclature for semi-path and semi-cycles. First, a non-directed walk or semi-walk is a digraph with a sequence of 1 or more nodes. A semi-walk can travel the wrong way on a directed edge. A semi-path is a semi-walk in which each node is distinct, again with the possible exception of the end nodes. A semi-circuit is a non-trivial semi-walk in which the first and last nodes are the same and no edges are repeated. And a semi-cycle is a semi-circuit in which the only repeated nodes are the first and last. And so we can see figure 5.6 for that. For connectedness, a pair of nodes in a digraph is weakly connected if there is a semi-path between them, for example, nodes B and C in figure 5.6. The nodes are unilaterally connected if there's a path between them, for example, all the pairs of nodes in 5.6 except B and C. Finally, the nodes are strongly connected if there is a path in both directions. The digraph is weakly, that is unilaterally, strongly connected if every path of nodes in the graph is weakly connected. A pair of nodes is disconnected if there is no path or semi-path between them. So we're just talking about the possibilities of connectedness between different elements in a graph as the high-level point of view. So the adjacency matrix of a graph G, A of G, provides a mathematical representation of which nodes in a digraph are adjacent to each other. So this can be something that you would see laid out in a matrix, a 2-dimensional matrix showing the connectedness, but there's some other possible ways of how that could be laid out. So we have adjacency. So what is connected to something else? And then we have something that, what about reachability? If it's 1 or 2 removed, you have to jump between different points to get to the next node. You're trying to see what type of reachability that exists. And so a node Nj of G is said to be reachable from node Ni if there exists a path from Ni to Nj in G. So it's not right next door, but it may be 2 or 3 things removed before it gets to that point. Some more definitions for unary relationships and digraphs. Reflexivity. What this means in this context is that all nodes must have loops. The top of figure 5.7 shows a reflexive relationship. Irreflexibility. This means that no nodes have loops. The relationship shown in the digraphs of figure 5.1 and 5.3 through 5.6 are irreflexive. The bottom of figure 5.7 is also an irreflexive relationship. So here is figure 5.7, and so here we have a sample of a reflexive relationship, and here is an example of a irreflexive relationship. It's you just go one way, and that's it. Then we have symmetry, asymmetry, and asymmetry. Symmetry, anti-symmetry, and asymmetry. And so these are just different ways of how things can be related. So for symmetry, there must be a cycle between any 2 nodes that are adjacent to each other. Asymmetry, anti-symmetry, there cannot be a cycle between any 2 nodes that are adjacent to each other. And for asymmetry, there can be no cycle between any 2 nodes, and there can be no loops. We have transitivity and intertensivity. Transitivity is the condition only applies to triplets of nodes and requires that there be a semi-cycle among 3 nodes in triplet. And for intransitivity, for X, Y, and Z, the relationship are either transitive or intransitive. cycles can either be transitive relationships, but note that a transitive relationship with 3 or more nodes means that there must be a cycle between every pair of nodes that is part of the cycle, resulting in a symmetric relationship with loops for the subset of nodes in the cycle. So here are some of these figures. You can find them in the text, but with the last couple of charts, there were references to 5.8, 5.9, and 5.10. And so here in 5.8, we have the digraph of a symmetric and intransitive relationship. 5.9, we have a digraph of a transitive relationship. And for 5.10, we have a transitive version of the digraph in figure 5.8. Ordering relationships. Relationship R is a partial order of set A when R is reflexive, antisymmetric, and transitive on the set A. In this case, A is called a partially ordered set or posit written A semicolon R. Therefore, a relationship that is partially ordered cannot have any cycles. 2 elements A1 and A2 and A are said to be comparable under R if either A1 are A2 or A2 are 1. Otherwise, the elements are incomparable if every pair of elements is comparable. And that means that they're totally ordered. There's some more complicated diagrams. And a Hasse diagram is an undirected graph of the relationship between the elements of a partially ordered set. And so here we see an example here of a Hasse diagram. So it's not a digraph. And then there's a second, here's just another example of a Hasse diagram. And so you can see that up below there. Isomorphisms, 2 graphs G1 and G2 are isomorphic if there exists one-to-one and onto functions between them. So I'm just going to continue on. I know there's a lot of definitions here, and so just to be thinking about it. Trees is probably a concept that's going to be a little bit easier to be thinking about. This next chart will show some examples, a sample tree, a non-directed tree, and a directed tree. Tree is a graph G with no loops. A rooted tree is a tree in which there is a designated root, and a directed tree is a rooted tree in which there is a directed path from the root to every other node. So those are just a couple of examples. And trees is an interesting topic that can be something we could spend a lot of time on. So there are a variety of statements that help us to be thinking about that. A directed tree is a graphic representation of a partition, the fundamental construct of our requirements, functional and physical decompositions. And then we have a couple other supporting things there, definition-wise for trees. So a spanning tree, a graph, a spanning tree that is a directed tree is a directed spanning tree. And so now we're introducing this idea of a spanning as well as directed. So a graph H is a subgraph of graph G. That is that the nodes in the subgraph must be a subset of the nodes in the graph, and the edges in that subgraph must be a subset of those in the graph, with the added stipulation that all of the edges are connected to 2 nodes, one on each end of the edge. We also have some more definitions here for a proper subgraph, a spanning subgraph, and a directed spanning tree. So I'm not going to read this whole slide, but those are just some more things that are relevant for trees, spanning trees, and directed trees. We can have quasi-strongly connected and quasi-strongly connected digraph. So these are some other things that can help us in our exploration of trees. And so the details here are spelled out on the chart and also in the text in Booty. So here is an example of a directed, in terms of directed trees, a quasi strongly connected digraph. So note that A and D are quasi strongly connected via E, and B and C are quasi strongly connected via both E and F. A and B are quasi strongly connected via E by considering the path EAB, as well as the paths from E to A, from E to F and to B. A directive tree can be formed with E as the root. So those are just some of the relationships between these elements and the relationship between a digraph and formulating this information as a tree if we wanted to do it that way. The height of a directed tree is the length of the longest path. And so here we can see that we can go from level 0 to level 4 for this type of a tree structure. A directed forest is a collection of directed trees. Forests are important in system engineering as we practice concurrent engineering. Recall from chapter 1 that we must be concerned not only with the system that will be used during the operational phase, but also with the development, manufacturing, training, deployment, refinement, and retirement system. The concurrent requirements form a requirement forest. And so here we have 3 trees within this forest. So now we'll talk about cycles and semi-cycles. In very large digraphs, it will not always be apparent that there are cycles or semi-cycles. To find the cycles, remove all the barren nodes, that is nodes without children, and border nodes, nodes without parents. Continue this process until there are no remaining barren or border nodes. If there are any nodes remaining, there are one or more cycles, and the remaining nodes are part of at least one of the cycles. To find the semi-cycles in a digraph, first replace all of the directed arcs with non-directed arcs. Then remove all the nodes of degree 1. Continue this process until there are no more remaining nodes of degree 1. If there are any nodes remaining, that there are one or more semi-cycles, and the remaining nodes are part of at least one of the semi-cycles. Okay, I'm just going to quickly go over this, but this is an example of a design analysis, if you will, for a city that had multiple rivers and a handful of bridges. And the goal is to travel across every bridge without crossing any bridge more than once. And so you can be thinking of a system engineering challenge like this. Maybe that is a functional way, that's how you're going to flow through the elements of your design, that you can only go through one function and only a single time. And so then this gets into something called a Euler path, and this is something that contains every edge. So there is a couple different ways that you can be thinking about this. You can be putting this into this type of a model. And so here is just looking at those various bridges and these various locales and how you're trying to connect them. And so I think that's enough for what I wanted to describe there. And so a Euler circuit as a graph G is a simple circuit containing every edge of G. So every point in this is you actually get to every edge, is what that's trying to suggest. So the graph G1 has a Euler circuit. Neither G2 nor G3 has a Euler circuit. So maybe this would be something for you to be thinking about if you want to explain that further. All right, well, let's just summarize this. And then there are some backup charts that I won't go through, but here is what we talked about in this chapter. A graph consists of nodes, that is vertices and edges. Edges define a relationship for the nodes. The relationship can require an order of the nodes so that the edges are directed. Directed graphs are the most applied in the engineering of systems. Bipartite graphs, which are a special type of directed graph with two or more types of nodes, where the edges cannot connect nodes that are of the same type. Sequences of nodes in a graph can be defined by the term walk, path, trail, circuit, and cycle. And we have definitions for each of those in this chapter, and also what we showed briefly in this lecture. Graphs can be connected or disconnected. There are variations of connectedness ranging from weakly to strongly. Nodes not adjacent in a graph can be reachable via a path in the graph. Reachability can be critical if attaining some output requires the execution of a set of functions, but the set of functions is not a part of a reachable set. The properties are reflexivity, irreflexivity, symmetry and asymmetry, antisymmetry, asymmetry, transitivity, and intertensivity from chapter 4 are redefined in terms of graphs. Visualizing these relationships provide a much greater understanding of their meanings and ability to detect their absence or presence in a graph. Partial ordering of the elements of a set are defined as alternative orders of the nodes based upon the relationships defined over the nodes. The Hasse diagram is defined and illustrated for finding the partial order on a set and then enumerating the possible partial orders. Trees and several variations of trees were introduced as a special form of a graph. A directed tree describes the notion of a hierarchical decomposition. Hierarchies of requirements, functions, and components were discussed in chapter 2 and will be revisited in chapters 6 through 11. These hierarchies must be partitions as defined in chapter 4 and can be represented as directed trees. So I think that's it for that. I'm not going to go over these more detailed diagrams, charts for IDEF 0. So that's for reference. And so you may want to just spend a little bit more time going through the textbook and reading some of this summary of these last few charts to get a concept of why we talked about discrete math and graph theory and how that potentially could be useful for a tool as we continue our journey in our exploration of system engineering. Okay, thank you very much, and that will end our lecture.